Hi, everybody. My name is Hari Subramanian. I'm thrilled to meet you in this privacy explainer open house. This is a new format of an open house for us. So we are sort of super thrilled to bring this to you. Um, what we're going to talk about today is a very light, high level sort of overview of what is privacy and why is it important to us. So let's, without further ado, jump right in. Every day we leave behind digital footprint as part of everything that we do. When you go withdraw cash from an ATM, you make a digital payment, visit a doctor, order groceries online, and have them delivered. All of that generates a data footprint. This data is powerful. It can make services more efficient for you, it can personalize products and experiences for you, and even drive medical breakthroughs. But it can also be misused to profile people unfairly, bombard them with creepy advertisements, or even expose people's identities. So the big question is, how do we unlock the value of data without giving out privacy? So what is privacy? Privacy is often misunderstood as secrecy, but it's not about hiding it. Privacy at its core is about control. It's the ability to decide which parts of your digital life do you want to share, and with whom do you want to share, and for what purpose do you want to share. Some data is harmless, like what is the weather outside today. Other data can be deeply sensitive and personal, like your medical records or your financial history. And privacy isn't just a one-time choice. Data has a life cycle. It's collected, used, stored, and finally can be deleted. At each stage, privacy has to be respected. If not, it can be entirely lost. Now, the most common way to protect one's privacy is this concept called consent. Consent is the most basic control primitive. It's how people decide how their data gets used. In fact, it's been around from the non-digital days when actual paper trail data was collected. But once collected, there is no control on who, when, and how it's shared. Consent changed that. When you install an app, and it asks for access to your camera or accelerometer, or when a bank asks for permission to share your salary details for a loan, all of that is consent at work. To be precise, there are two types of consent: consent to collect and consent to share. But oftentimes, they actually get clubbed together into a single step. Here is the problem. Under global frameworks like GDPR, consent has been defined as a coarse-grained primitive. A data processor, an entity that gets consent for collecting data, also enforces the consent for sharing the data with interested parties. And when the same party is responsible for both, for collection of your consent and for sharing and enforcement of the consent becomes blunt. It's either a blanket yes or nothing. You hand everything over or you get nothing at all in return. It leaves people with little real choice. It's a Hobson's choice. And this model hasn't scaled really well globally. When India looked at this model carefully when building its account aggregator ecosystem for financial data sharing, we did not like what we saw. So we did something very different. We moved all of the controls to sharing, not collection. So it's as close to the inference point as possible. Then we unbundled consent. We separated collection of consent for sharing and from the enforcement of the consent for sharing into two distinct steps with different roles and actors. Here's how it works. Consent for sharing is collected by account aggregators, which act as a trusted agent of the individual. You can, in fact, pick one of many account aggregators in the market, whichever one you trust. Enforcement, however, happens downstream by entities named as the financial information users. These could be banks, NBFCs, or wealth advisors. And that enforcement happens under the oversight of this account aggregation ecosystem. And crucially, enforcement is not left to chance. It is built into the protocol itself. This is what we call techno-legal, the next concept I'm introducing. Combining law and technology so that legal promises are enforced automatically by code. The result is a state-of-the-art, granular, purpose-limited consent mechanism. In India, consent is no longer one-sided. It's two-sided. The consumer collects it and the system enforces it. Consent here is not just a promise, it's something that gets checked, enforced, and logged and audited automatically. This model, since the launch of the account aggregators in 2021, has continued to innovate and improve consent for sharing into concepts like delayed consent, where the collection or activation of consent is delayed to a point where the true value has already been established for the individual in question, further optimizing this process. Stay tuned for an exclusive open house that we're going to be doing on delayed consent soon. Now, consent works beautifully for inference, where data is used for a one-time decision, like a bank checking your last 6 months of transaction record to decide whether to grant you a loan or not. What about training, though? Here is the key difference. Inference is when a model uses data to make a decision about one person. But training is when a model is taught to use thousands, or in case of India, millions and tens of millions of records to learn general patterns that exist inside that data set. Inference is like asking a student a single question, whereas training is like, say, teaching the whole class or throwing a quiz or a national level talent search contest to a very large population of students. Consent works well for inference because the decision is specific and momentary. But for training, it breaks down. It is impractical to reconsent millions and millions of people every time a model is updated. Nobody would want to do that. So, what is the solution and what is the control primitive for training? Training uses massive data sets. You cannot realistically ask every person for permission. We already talked about it. Whereas models can sometimes memorize private information. If a phone number or a medical record is in the training set, model might memorize that information and spit it back out just as part of regular inferencing at a later point in time. There is no control that you have on it. People have forever tried techniques like anonymization is a very popular technique. The idea there is just remove names and any other PII information and the problem is solved. But anonymization oftentimes fails because it is an art, it's not actual science. Imagine a data set with age, zip code, medical condition of patients, and other fields in its data set. Even without names, if you strip out the names, if there's only one 43-year-old in that zip code that has a particular medical condition, it's easy to re-identify the person. Typically by combining data sets and then joining those two data sets. Say in this case, you're able to find data set of all people who own a property in that same zip code, and there happens to just be one 43-year-old, but you get the name from that record. You can now reverse engineer by combining these data sets and re-identify that person. Anonymization is like putting sunglasses on. It hides a little, but it's not enough. So just like consent is the control primitive for inference data, we need to ask ourselves, what is the right control primitive for training data? Until 2006, we did not have a great alternative. Then researchers from Microsoft introduced a breakthrough idea called differential privacy. Differential privacy gave us a new control primitive for training. That's the privacy budget. Here is how it works. Instead of relying on consent for every record, you set a privacy budget at the start when the data set is actually created, all the way in the beginning of the process. Each time data is used, a bit of that budget is consumed, and the budget determines how much information can be safely revealed from the data set, no matter how many queries or training steps are run. Compare this to, say, a credit card with spending limits enforced on it. Once the limit is hit, no more transactions are allowed on it. So this is the spending limit for privacy. Once the budget is used up, no more queries can actually drain privacy from that data set. Differential privacy can add controlled blur to these results, in that DP actually balances between privacy and utility of the dataset. Imagine a group photograph. With differential privacy, the picture is slightly blurred. You can see the overall pattern, but you cannot recognize any single face. You add too much blur, the picture becomes useless. That's the utility angle of it. But add the right amount of blur. You can actually see important details like the number of people, maybe even the mix of men, women, and kids in that group, patterns of maybe how they're standing or laid out in that group. But they're all in the picture, but you cannot see their faces. This privacy budget is the alternative control primitive for training. Just as granular consent enforces control in the inference cycle, the privacy budget enforces control in the training cycle. Granularity and purpose limitations are hard to enforce with consent, but they're practical with privacy budgets. Look for an exclusive open house that we're going to be doing, and that's going to be a technical deep dive into privacy budgets and epsilon. And epsilon is essentially this sort of flexible knob that allows you to control the amount of privacy and utility and do that trade-off for each data set. So now we have two primitives: consent for inferences and privacy budget for trading. But how do we enforce all of this in practice? That's where confidential clean rooms, or CCRs, come into picture. Think of a CCR as a privacy vault, if you will. There are three components that work together to make up this privacy vault. First one's, of course, differential privacy. We looked at it in detail. Second concept is called an electronic contract. It's a machine-readable rules that define who can use what data and for what intent or purpose. And then the third one is confidential compute. It's a sealed digital environment where data can be processed, but it can never leave raw. Together, electronic contract plus confidential compute plus differential privacy make up for a CCR. This makes collaboration with data and working together with data for multiple entities safe to do. Organizations can contribute data, train models, and analyze insights, while only privacy-preserving results can be taken out. And every action is logged and it's auditable inside a CCR. Let's do a slight deeper dive into two of the concepts we saw. First, electronic contracts. Electronic contracts are like rule books or recipes for the CCR. They specify who may use what data and for what purpose, under what privacy conditions, and potentially even for how long. Right? All of that detail is encoded electronically into these recipe books called electronic contracts. Unlike traditional contracts, electronic contracts are machine readable. They can be enforced automatically by the system. If the contract says data can only be used for research, the CCR will reject any attempt to use it for, say, marketing. Now, the next concept we will deep dive into is confidential compute. Confidential compute is, think of it as a sealed chamber of the CCR. Data enters encrypted, it's processed within the confines of the secure enclave, and only approved results can leave the confidential compute infrastructure. So think of it as like a locked kitchen, if you will. Ingredients are brought inside in sealed packages, so you cannot see what information goes in transit. Cooking happens behind, say, frosted glass, so you know that it's secure and being prepared in front of your eyes, but you cannot see what is the recipe and how it's being cooked, or what is the process, because that could be a trade secret of the kitchen itself. And what leaves is a finished dish accompanied by a signed receipt confirming that the recipe was followed to the T. Therefore, you are confident in the outcome of this process. That is confidential compute. CCRs also enforce something called purpose limitation. Purpose limitation is a cornerstone of privacy law. Data may only be used for the purpose for which it was collected. For example, you might allow your health records to be used for medical research, but you don't want to be marketed, products and services using the data. In traditional systems, purpose limitation oftentimes relies on trust that I shared the data for this intent. The organization that's using the data is going to use it for the right purpose. However, in CCRs, it is encoded into this electronic contract, enforced by the confidential compute, and mathematically supported by the principles of differential privacy. If someone tries to use the data outside of the stated purpose, the system can block it, record the attempt, and notify auditors. This turns promises into guarantees in the system. Now, when consent, privacy budgets, CCRs, and purpose limitation, all of these are combined together, we achieve something that we refer to as privacy-preserving data training. It's auditable. Independent checks confirm the rules were followed. It's provable. Math guarantees that the individual details are actually hidden and private and remain that way for the life of that model. And it's scalable. It works across millions and tens of millions of records in a country like India. It's practically possible for you to build systems using this methodology. This finally allows us to train powerful AI models without sacrificing the privacy of the individuals that are inside that record. Of course, technology alone is not going to be enough for bringing this all to life. Governance is critical. That's where data collabs come in. Think of them as cooperatives for data. Different stakeholders, data providers, data consumers, users, auditors, regulators, all come together under shared rules of the system. Self-regulatory organizations accredit CCR operators. These are people who can operate the special purpose infrastructure that is CCR, and they can be cloud operators or cloud infrastructure providers. Auditors evaluate and set privacy budgets for data sets. They review logs, ensure compliance. Regulators, if you're talking about data collabs that operate for regulated industries, set the legal framework that is required for their vertical industry. And participants agree to electronic contracts that encode these rules. This creates trust not just through technology, but also through institutions and governance in place. As AI begins to create content, news articles, images, and even legal documents, new challenges are going to emerge. Who created this content? How was it modified? Who is accountable for its effects? And what do we do if we find a privacy violation? How do we get rid of it effectively and permanently? AI chains provide the answer. That is the next concept that we are introducing. They record the provenance of AI generated content through immutable records that are part of blockchain, a chain of custody that shows where content came from, which model generated it, and how it has been altered if it's been altered. But provenance alone is not enough. Techno-legal protocols must also authenticate content, tying digital artifacts to their provenance records in ways that are verifiable and enforceable. With provenance and authentication, liability now becomes enforceable. Harmful or illegal content can be traced back to the systems and actors that are responsible. Stay tuned for an exclusive open house that we're going to be doing on AI chains very soon. Now, I know what you're thinking. Now, are these all just concepts or is this even real, right? Let's see this coming together in action in a marketing tech example where privacy is not just for protecting data, it can also make business cheaper and more efficient. Let's say a bank wants to build a new credit card for online shoppers. Instead of paying for ad networks, it perhaps wants to collaborate with a e-commerce company which already has online shoppers that would love to get their hands on this shiny new credit card. The electronic contract states to use the data shared only to train a credit card model. Confidential compute is going to process this data in a sealed environment, so there is no leakage of privacy from the compute environment. Differential privacy is going to enforce the privacy budget so that the information that is shared inside the PII information is not going to leak in an undesired manner. And auditors are going to sign off on the results. Banks get privacy safe customer segments, lower acquisition costs, and higher relevance, and no raw data leaks, while consumers actually get access to really relevant offers that they care about without spammy ads. The bigger picture that emerges from all of this is, for inference, India has redefined consent as a granular, two-sided techno-legal primitive. For training, however, differential privacy has been introduced along with privacy budget as the primary control primitive. And with confidential clean rooms combining electronic contracts, confidential compute, and differential privacy, both inference and training can be enforced automatically. And add to that governance through data collabs, you now have a framework that makes privacy auditable, provable, and scalable in nation scale. This is the next frontier of digital public infrastructure. It shows the world that privacy and innovation are not opposites. You can have both in this model. Now, that's a wrap, folks. It's been fun walking you all through this privacy explainer, and I hope you all enjoyed it as well. Until next time, signing off, this is Hari Subramanian.